Hey there and welcome. Ever wonder how your phone knows exactly where you are or how your watch always has the right time no matter where you go? Well, today we're pulling back the curtain on the amazing invisible grid that wraps around our entire planet.
So let's just start with a fundamental question. Where on Earth are you exactly? I mean, think about it. If you were trying to meet a friend in the middle of the ocean, how would you even begin to tell them where to find you? It's a massive problem, right? How do we give a precise, unique address to any single point on this huge sphere we call home?
Well, the solution, figured out over centuries, is actually kind of brilliant in its simplicity. We just wrap the entire Earth in a grid of imaginary lines, and where two of those lines cross, you get a unique address, a specific pinpoint location. This whole system is built on two big ideas: latitude and longitude.
Okay, let's start building this grid. First up, we've got the horizontal lines. A great way to think about them is like the rungs of a ladder, letting you climb up and down the globe. This is latitude.
Now, the technical definition is that latitude is an angle measured from the Earth's center. But what you really need to know is that these lines all run parallel to each other. They never, ever touch. And, that's exactly why they have another name: parallels. Makes sense, right?
Our starting point, our home base for latitude, is the equator. That's at 0 degrees, and it splits the Earth neatly into the northern and southern hemispheres. From there, you have other key lines you probably heard of, like the tropics of Cancer and Capricorn, all the way up to 90 degrees north at the North Pole and 90 degrees south at the South Pole.
So what's the whole point of these lines? Well, their main job is to measure distance north to south. And here's the magic number you're going to want to remember. For every 1 degree of latitude you travel, you've covered about 111 kilometers. Super useful.
Okay, let's put this into practice. Say we've got two cities, both in the northern hemisphere: Lagos, Nigeria at 4 degrees north, and Cairo, Egypt sitting at 30 degrees north. How could we use latitude to figure out the straight line distance between them?
You're going to love how simple this is. First, you find the difference in their latitudes. Since they're both in the north, you just subtract, so 30 minus 4 gives you 26 degrees. Then you take that 26-degree difference and multiply it by our magic number, 111 kilometers.
And there it is, 2,886 kilometers. That's about how far apart Lagos and Cairo are. It's pretty amazing when you think about it. A few simple rules let us measure our entire world.
All right, we have our horizontal rungs for the ladder. But now we need the vertical lines to complete our grid. So let's talk about longitude, which does something completely different but just as important.
So if latitude lines are like the rungs on a ladder, a good way to picture longitude lines, or meridians, is like the slices of an orange. They all run from the North Pole straight down to the South Pole, and they all converge at the ends. Their job is to measure how far east or west you are.
And just like the equator is a 0-degree line for latitude, the prime meridian is a starting line for longitude. Back in 1884, a bunch of countries agreed that the 0-degree line would pass through the Royal Observatory in Greenwich, London. And honestly, the main reason was that most of the world's sea charts were already using it as a reference anyway, so it just made sense to make it official.
Now, this is where longitude totally changed the world. See, its main job isn't distance, it's time. For centuries, sailors could figure out their latitude from the sun, but longitude was this deadly mystery. The solution turned out to be a really accurate clock. The Earth rotates 360 degrees in 24 hours, which means it turns 15 degrees every single hour. Longitude is literally a clock for the entire planet. Let's put this to the test. Imagine it's exactly 12 noon on the prime meridian, right there in London. What time would it be in a city in Brazil which is located at 50 degrees west longitude? All right, the math is pretty straightforward. The longitude difference is 50 degrees. We convert that to time by dividing by our key number here, 15 degrees per hour. So 50 divided by 15 gives us 3 full hours. With a little bit left over, that works out to 20 minutes. So a 3-hour and 20-minute difference. And this part is key because the city is west of London, its time is earlier, so we have to subtract.
So you take 12 noon, you go back 3 hours and 20 minutes, and you get 8:40 in the morning. While London is having lunch, that city in Brazil is just starting its workday, and it's all thanks to longitude.
Okay, so now we get to two pieces of the puzzle separately. Let's bring them together and see how they create this complete global positioning system.
So let's just do a quick side-by-side. Latitude lines are parallel, but they get shorter as you head to the poles.
Longitude lines are all the same length, but they all meet up at the poles. Latitude measures distance north-south. Longitude determines local time. It's a perfectly complementary system.
Now this system has one more really cool concept we should talk about: great circles. A great circle is any line that slices the Earth into two perfect halves. The equator is the only line of latitude that's a great circle. So why does this even matter? Well, here's the secret. The shortest distance between any 2 points on the globe is always along a great circle route. It's why a flight from New York to Tokyo goes way up over the Arctic. It looks longer on a flat map, but it's actually the shorter path.
You know, this whole connection between longitude and time has some really fascinating real-world consequences. It's what gave us time zones, and one of the absolute strangest lines you'll ever see on a map.
To stop every single town from having its own slightly different local time, which would be chaos, we created a standardized system. We use Greenwich Mean Time, or GMT, as our global reference point. From there, the world is divided into 24 time zones, mostly following those 15-degree chunks of longitude, so we can all agree on what time it is.
But that makes you wonder, right? What happens on the complete opposite side of the planet from Greenwich? Well, right around the 180-degree meridian, we find the International Dateline. And that is the official start and end of the calendar day.
And this is where things start to feel a little bit like science fiction. If you cross this line heading east, you jump back a day. You literally get to live the same day twice. But if you cross it heading west, you skip forward a day entirely. It's pretty much the closest thing we have to time travel.
So the next time you check your phone for a map or try to figure out the time difference for an international call, just remember this elegant, invisible grid. It's a system of imaginary lines, a solution to an ancient problem that still defines our